Hi, it's Peyton again. Heard you needed a hand with functions and their inverses. Let me see what I can do for you. There are several special properties about a function's inverse. One is that the domain for a function will become the range for the function's inverse, and it works the other way around. The range for the original function will become the domain for the inverse function. Now remember that the domain of a function is the interval or intervals of which the function is defined on, and the range is the interval or intervals, the y values that the function is defined on. To work our way through our topic, let's approach it first graphically. The previously stated properties are best known with a well-known function and its inverse. The function is y equals e to the x, and its inverse is y equals natural log of x. First, let's look at a graph and then the domain and range of each function. Here's a graph of y equals e to the x, and its domain and range are this. The domain is all real values, or x from negative infinity to positive infinity, and the range is y exists between 0 and positive infinity. And now let's look at its inverse, natural log of x. Here is the graph for that, and its domain and range are this. The domain is 0 to infinity, x lives between 0 and infinity, and the range is negative infinity to positive infinity. Now let's look at the two charts right next to each other, the domain and range. We can see by looking at this chart that we have on the left y equals e to the x, and we have the domain and range, and on the right we have y equals natural log of x. We can see that the domain and range are flipped between the functions. We can see that the domain for y equals e to the x is the range of y equals natural log of x. And the same way with the range. The range for y equals e to the x becomes the domain for natural log of x. Okay? Now let's take a peek at the graph to see how we can see this relationship. On this graph I have both functions mapped. I have e to the x in red, and then I have natural log of x in green. Now, in order to see this relationship, I'm going to put one more function on there, the line where y equals x. And this is what that graph will look like. Now imagine if we were to take our graphing paper and folded it along that line, y equals x. If we did, the two graphs would overlap each other. They would be the same. And they're mirror images across that line. Now, this is great, and it's supposed to happen. Now, remember how we flipped the domain and range a second ago using the tables? Graphically, that's exactly what we're doing, folding across this line. But be careful, because the folding trick doesn't work for all functions, but we'll get to that in a second. Now let's look at a different example. Y equals 4x minus 9. We aren't told what its inverse is, but we can determine some information about the inverse's domain and range, and let's look at that. For the original function, the domain is all real values, or x lives between negative infinity and positive infinity, and the range would be all real values as well. Y exists between negative infinity and positive infinity. Now we can use a trick we learned before about just flip-flopping those. So for the inverse, the domain will be the range of the original function, so all real values. And then the range for the inverse function will be the same as the domain for the original function, which will be all real values as well. Now let's look at a graph of our function. This is the graph for y equals 4x minus 9. And now I'm going to put the line y equals x on this graph. And then we're going to fold our original function across that line to find the inverse function. And that's this graph here. Okay? The red line is our original function, the green line is our inverse function, and the brown line is the function y equals x, our folding line that we're worried about. Okay? This folding method is the way that we can look at the domain and range of an inverse function and find the inverse graphically. Now let's move to the algebraic method of finding the inverse. And this gets a little hairy, so just bear with me. Algebraically, there are two steps. The first step is we switch the x and the y. So where there's a y, we replace it with an x, and where there's an x, we replace it with a y. Okay? And then the second step is just solve for y. Make it a y equals some function of x. Okay? Let's look at that first example I showed you. that dealt with y equals e to the x and y equals natural log of x. First, we want to find the inverse of y equals e to the x, and algebraically it should end up being y equals the natural log of x. Step 1, we want to switch the variables, so y equals e to the x becomes x equals e to the y. We've just flipped the variables, we've just interchanged them. Step 2, solve for y. We want to isolate the y, we want to bring it down. So we'll have, currently our equation is x equals e to the y. We're going to hit both sides with a log, and that'll bring the y down. Then our equation becomes natural log of x is equal to natural log of e raised to the y power. The natural log will bring the y down in front of the natural log, so we'll have the natural log of x is equal to y times the natural log of e, and the natural log of e is 1. So then our equation becomes y equals the natural log of x. And that's the inverse that we showed earlier. Let's work another example and find the inverse of the function we're given. The function is y equals x squared minus 9. So our first step should be to flip the variables, so I'm going to do that, and we'll interchange x and y, so it will become x is equal to y squared minus 9. The second step will be solve for y. To do so, I will add 9 to both sides first, so it becomes x plus 9 is equal to y squared. And then I will take the square root of both sides to isolate y. So then the question becomes, y is equal to plus or minus the square root of x plus 9. Off the bat, we can tell that this isn't a function because there are two functions embedded there because of the plus or minus square root. Let's look at it graphically to get another idea of why it's not a function. And here's the graph of both of those. One is the graph of the positive square root of x plus 9, and the other graph is the negative square root of x plus 9. We can test to see if it's a function using the vertical line test, and all we need to do is just draw a perfectly vertical line, a line that's running up and down, and we see that it touches the graph in two places. If it does that, it fails that test and is therefore not a function. But we need to ask ourselves, does the equation y equals x squared minus 9 have an inverse function? And the answer is it doesn't, because it fails that vertical line test. And we can find that either graphically or algebraically. We can see this a little bit better with our next method, and that's using tables to find the inverse function. With this method, we get something similar to a cheat. Remember earlier how I showed you graphically that a function's inverse is just a reflection across the line y equals x? We're going to capitalize on that and see a pretty neat little trick. When we flip the original function over that line and find its inverse, we exchange the domain and range, and a little bit more unknowingly. We also exchange the x and y values of each coordinate point. So to elaborate on this a little bit more, let's use my first example again. Y equals e to the x, and its inverse y equals natural log natural log of x. And here's the graphs. And the graph in red is e to the x, the graph in green is natural log of x. And now let's pay close attention to where e to the x, the red graph, crosses the y-axis, and that's at the coordinate point 0, 1. Now look at where the green graph, natural log of x, crosses the x-axis. That's at the coordinate point 1, 0. Okay? Now, if we stick to what I said earlier about flipping the coordinate points, this holds true here too. And let's look at a table of values. And here's a table. We have e to the x on the right, and we have natural log of x on the left, and their x and y values. And we can see, looking at that, when x is negative 2 for e to the x, the y value is 0.13534. And then on natural log of x, when the x value is 0.13534, the y value is negative 2. We've just flipped the x and y values. And you just go down the list and you can see that flip. Okay? Now, remember the y equals x squared minus 9 example? Two x values in the original function go to the same y value. And that's because of that parabolic shape, that U shape that they have. When we flip the coordinate points, which x value gets the y value? Who gets who? And that's the problem with that example. It's not one-to-one and therefore cannot have an inverse function. Here's an example using tables. Given the following table, determine as many coordinate points of the inverse as you can. And here's the table. We have x from 4 to 10, and we're given the corresponding y values. Okay? To find the inverse function, to find the inverse table, all we have to do is just flip the x and y values. So we'll write another table, and for the inverse, the x values will just become the y values. And then the x values of the original function will now become the corresponding y values of the inverse function. And so in the original function, when x is equal to 4, y is equal to negative 32. In the inverse function, when x is equal to negative 32, y is equal to 4. Okay? That's pretty easy, and you can go down the list doing that each way. Okay, let's look at another way of using tables, and this time we're going to use a diagram. Here's just a diagram of some function f of x that maps some x's to some y values, and here the x values are 3, 5, 8, and 12. And f of x maps 3 to 7, it maps 5 to 2, it maps 8 to negative 6, and it maps 12 to negative 10. Okay? We're asked to find the inverse of this function. And so all we have to do is just flip the x and y values. So the x values for the original function now become the y values of the inverse function, and the y values of the original function now become the x values of the inverse function. Okay? And I've flipped this in my new diagram, and so my x values now are 2, negative 6, 7, and negative 10. And I have to map these to the correct y values. And so here I have to map 2 to 5. So f inverse of 2 would be 5, because in the original function, 5 maps, f of x maps 5 to 2. Okay? And all you have to do is flip them and just make sure the values are correct. Let's do a recap before we go. Here are several methods to find the inverse of a function. The first method is graphically. Here all we do is reflect a function across the line y equals x, and we make sure that we interchange the domain and range correctly. There's the algebraic method, which we do by reversing the variables and then solving for y equals some function of x. And then there's using tables, and there all we do is we just interchange the x and y values and make sure that they correspond to the correct value in the inverse function. I've given you all you need to approach inverses. I'll catch you next time. Good luck.